The binomial theorem comes in handy when we have a situation like this. When we have x plus y all to the n. Now these can be real numbers, rational numbers, any kind of numbers. And then the theorem gives us that x plus y to the n is equal to the sum from k equals 0 to n of n choose k, x to the n minus k, y to the k. If you write out the series notation, you get that it equals n choose 0, x to the n, plus n choose 1, x to the n minus 1y, and so on and so forth, until you get to the final term, which is n choose n, or y to the n. Let's try a quick example to make sure we understand. So let's look for the coefficient of x squared in 2 plus x to the power of 357. Now, obviously, we would never expand this out by hand. That would be ridiculous. It would take a very long time to figure out the coefficient that we want. So instead, let's use the binomial theorem. So 2 plus x to 357 is 357 choose 0, 2 to the 357. 357 choose 1 times 2 to 356 times x, and so on and so forth. Which all we're doing is we're just substituting our x and y. So in our case, our x is actually 2, and our y is actually x. And all we're doing is substituting that in, and we notice that this is our x squared coefficient. You can calculate 357 choose 2 on your calculator. There should be a button for it somewhere. Check the manual if you're unsure. In our case, 357 choose 2 is equal to 53,301. And we have this 2 to the 355 here as well. And so that's our coefficient. And so you see how easy this is to get any particular coefficient that we need. Obviously, this 357 is quite a large number, and your calculator might not be able to handle it. So for example, if you chose 357, choose 100, most modern calculators can't deal with that, although there are many computer programs that you could use to calculate it if you didn't need that answer. Now that we've had a look at the theorem, and we've seen an example, let's have a look at the proof. So in this case, we're going to use induction, and we're going to start from n equals 0. So let's check our base case. X plus y to the 0 is equal to 1, which is equal to 0 choose 0, x to the 0, y to the 0. Thus, we've established our base case. Now, let's assume it's true for some n in the natural numbers, and consider x plus y to the n plus 1. Now, taking one of these terms and splitting it in two, we get that this is equal to x times x plus y to the n plus y times x plus y to the n. Now, we can use our assumption here and write these terms as stated in the binomial theorem. Then what we can do is we can absorb this y and this x into their respective series. So we end up with the following. The next step is to take the final term from this series, which if you plug k equals n into here, you'll see that the final term is y to the n plus 1. So we're going to take that from this series, we're going to decrement the series here by 1, and we're going to put that y to the power n plus 1 over here. We're going to do a very similar sort of thing with this series, except we're going to take the first term when k equals 0. And again, if you do the calculation, you'll see that we're taking this x plus 1 term out of this series, and we're increasing this to k equals 1. Now we're going to do some manipulation with these series to see if we can merge them and then simplify. So the first thing we're going to do is we're going to shift the indices on this one by 1. So we're going to increase all k values by 1. So we see here we're starting on k equals 0. We're going to go to k equals 1 there. And the same thing over here from n minus 1 to n. So we've increased all of the indices by 1. At the same time, whenever k appears in here, we've changed it from k to k minus 1. So k, k minus 1. This is n minus k plus 1, since we had a minus k here. And k plus 1 to k. To see that these are really equal, you can plug in k equals 1 to here. So you'll get n choose 0, x to the n, y to the 1. The first term in here is n choose 0, x to the n, y to the 1. And you'll find the same thing happens if you put n minus 1 in here as well. So you'll see that these series really are the same thing. We haven't changed anything in the rest of the terms, so we'll leave those for now. We'll then notice that the series run on the same indices here. They run from k equals 1 to n, k equals 1 to n. And we also have these two terms here that can be grouped together. There's y to the k and the x to the n minus k plus 1. So we'll do that. We'll put these together in one big sum. If you're familiar with the choose notation, you might remember Pascal's identity. And what Pascal's identity allows you to do is to turn n choose k plus n choose k minus 1 into n plus 1 choose k. So we see here these two are turning into these. That's called Pascal's identity, and I'll provide a short proof of that at the end of this video. So, using Pascal's identity, we simplify this further, and now we notice that we have this n plus 1 here and n plus 1 here. This is starting to look good for our inductive step, since the series is looking very similar to the one in the binomial theorem, except with n plus 1, which is what we want. The next thing to notice is that if we were to plug in k equals 0 to here, we'd get x to the n plus 1, which just so happens to be this term over here. Equally, if we were to plug in k equals n plus 1 here, we'd get y to the n plus 1. So, if we absorb both of these terms back into the series, we get the sum from k equals 0 to n plus 1 of all of this. And that just so happens to be the form that we need it in for the binomial theorem to work. And thus we're done. Since we proved it was true for 0, and if it's true for n, then it's true for n plus 1. So therefore, it's true for all of the natural numbers by induction. If you wanted to see the proof of Pascal's identity, just have a look at this. So if we write out n choose k and n choose k minus 1 using their factorial definition, we can then get them over one common denominator by multiplying as necessary. And then simplifying the numerator gives us n plus 1 factorial divided by k factorial, n plus 1 minus k factorial, which just so happens to be the factorial definition of n plus 1 choose k. And thus we're done.